The tensor then generates a CLEE that needs to be added in quadrature with the CLEE of the scalar. The same for the TE. But now what is very nice is that we are generating a CLBB from the tensor, which has no scalar counterpart. So at this level, it sounds like we have a spectrum CLBB that would only come from tensors. Now, what is the shape of this contribution? Well, it depends crucially on the overall of amplitude of the primordial tensor spectrum. And a very interesting thing is that this overall amplitude depends directly on the time or the energy scale at which inflation took place. If it took place early at high energy, we have a very big amplitude for the primordial tensors. If it takes place later at a lower energy, we have less amplitude. So we usually parameterize this with a parameter R, which is a tensor to scalar ratio, which we try desperately to measure. And here I show you the different components for a tensor to scalar ratio of 0.1, 10%, which is already excluded by current data, but okay, it's not far from the current constraints. So we are in log scale because we want to have a look at very small signals. And in solid line, we have our CLTT from scalars. In dotted line, and for this R of 0.1, we have an equivalent shape for the tensor modes. And you see that for the tensor mode, we have a plateau coming from modes which are super-Hubble at decoupling, but then it goes down. So the overall shape is very different, which is good because it gives us a handle on a possible separation between the two signals. We know that their shapes are different, so if we measure the total, we can fit the total by a combination of these two templates, and from the deformation of the left part of the curve, we may find out that we have a contribution with such a shape. So this was the first method that was used to try to measure tensors. And the result was negative with WMAP, with Planck, from temperature. It seemed that the whole signal can be explained by the scalar contribution, which puts an upper bound on the gravitational wave. But the upper bound is not super accurate because at some point you cannot constrain this because it's hidden in your noise and it's hidden in your cosmic variance, especially in the cosmic variance. So we have already done all what we could do by using information from temperature. We know that this curve is low and we have an upper bound, and we cannot improve this bound because our temperature measurement for small l is dominated by cosmic variance. So we have to go to other signals. And the next thing you can do is go to the E mode. And for the E mode, there is a similar situation. For small l, the scalar contribution and the tensor contribution follow each other, but then the tensor contribution drops down. So you can try to do the same separation, but you will not get something more sensitive. But then the hope is to have a very good sensitivity in order to be able to measure signals with this amplitude, which is 6 orders of magnitude smaller than temperature. Because if you have a sensitivity corresponding to this level, and you decompose your map in E and B mode, you think that your B mode can only come from tensor, will not be masked by scalars, and thus you would have a direct handle on measuring the tensor modes. So that's a big hope. It could work. It still may work. It's tempered a bit by the fact that there is this green curve. The green curve is something we will describe later. It comes from CMB lensing. CMB lensing is a distortion of the patterns on the last scattering surface that you compute by going to the next order in perturbation theory. It's no longer linear perturbations. And the nonlinear equation that governs CMB lensing violate the idea that if you have only scalars, you can get only divergences. Because you go to one more order in perturbation theory, you can have more gradients and you can build a curly pattern. So because of CMB lensing, actually the E mode polarization gets lensed, the E mode map, when it gets lensed, becomes a distorted map with a bit of curly pattern, which you can interpret by saying that the E mode leaks into the B mode by lensing. So this green curve corresponds to the leaking of the blue curve from E to B mode because of lensing. Okay, there is still hope because this lensing contribution drops at small l more abruptly than the tensor contribution. So our bet is that if we look at a B map, if we can measure a B map on very large angular scale, and if R is not too small, this dotted green line, the B mode tensor signal, could still dominate the lensing. And we could still measure an R of 10 to the minus 2, 10 to the minus 3. Additionally, there is a way to partially get rid of this curve. I will come back to this later. So that's one of the main targets in current CMB physics, to detect B mode on small L's. This would help to put constraints on inflation. Usually constraints on inflation are shown in a parameter space where you have the tilt, you have the tensor to scalar ratio, and each category of model live in a region in this parameter space. And so by trying to see the B mode better and better, you put upper constraint on R and you try and you hope to detect it. For instance, this was a constraint, the blue contour was a constraint in 2015. The red one was in 2018, thanks to progress in BICEP and KEK. So we know already from this that the potential, or the part of the inflaton potential that we can observe is concave. But many models live with a very small r, like this famous Starobinsky inflation. So we would love to get better sensitivity to r through B modes in order to see this non-zero value of r here. And that's the purpose of a satellite like Lightbird. I can't resist you showing you something which is was not shown very much when it came out. It's a comparison of the contours between Planck and WMAP. And this was a contour on R and NS that you got from WMAP after 3 years of observation in 2006. The final release is from 2009. It's a bit better, but not much better. And then you see plots like this, and you don't really see how it compares to the other one because the scale is being changed. So I have actually done the careful job of matching the scales, and now I'm going to show you the Planck constraints. It's Planck plus, well, the blue is essentially Planck alone, and this one is Planck plus BICEP plus KEK. I don't know why we did not show it after the Planck results. I think it's because Europeans are not so good at marketing, because it's really impressive. Okay, so you see how the situation has improved drastically. And I don't tell you when I started my PhD. Okay. Okay, but still we are missing this detection of R. So we already touched a bit CMB lensing, and we saw in particular that understanding CMB lensing would be nice if we want to get better constraint on primordial B mode and clean this lensing signal. So I'm going to tell you a little bit how this business works. I start with this famous plot from Wayne Yu, which is just for pedagogical purpose. When you here simulates a little region in a temperature map, and then a little region in an E mode map. And then he assumes that when we look at these maps, between this direction of the sky and us, there is a very, very big cluster of galaxies centered, spherically symmetric, centered in the square. And for this purpose, the density of the cluster is exaggerated by many orders of magnitude in such a way that you go from the weak lensing to the strong lensing regime, and that you can see something by eye. So the idea is that the photon traveling from the last scattering sphere to us are deflected by the cluster. It produces a distortion, and what we should see would be something like this with funny patterns here. And even if we would not exaggerate the pattern. We could still say, by running some statistics, that far from the lensing effect, we have a Gaussian map. Close to the lensing effect, we have non-Gaussian patterns. The same with the E mode. This doesn't matter now. Okay, so let's try to build up a mathematical description of the effect. What we assumed so far in all the previous description was that between the last scattering surface and the observer, the photon travel exactly in straight line. We neglected lensing effect. This was not so stupid because we were trying to look at linear perturbations of temperature and polarization, which are already very small. Lensing is caused by metric fluctuation, which are also very small. So if we had tried from the beginning to take into account the fact that structures can distort the path of the photon, we would have tried to incorporate effects of order 2 in perturbation theory. And we started with order 1. So it was a good description. So now we go to order 2 effects, which are the impact of the small deflection on the already small anisotropies on the last scattering sphere. So we have two small quantities that will get multiplied with each other. Delta T over T rho is supposed here in my notation to be the delta T over T that we could measure if the photon would travel in straight line. So it's a delta T over T reflecting really the situation on the sphere. And because of weak lensing, what we see is a delta T ops over T, which has a one-to-one mapping with delta T rho, but with a deflection field. So this field is a vector field on the sphere. It's a two-dimensional vector field on the sphere, and it takes the different values in each direction due to the complicated distribution of clusters around us. Then there is again an argument, it's a bit like E and B mode, which says that if you are looking at leading order in perturbation theory and at the effect only of scalar modes, which are of course the most important one, then you can write these deflection fields as a gradient on the sphere of a potential, which depends on direction. And you call this potential the CMB lensing potential. I already use the letter small phi for the metric fluctuation, so I use a big phi for the CMB lensing potential. But in most articles focused on lensing, it would be the opposite. They would use a small phi for the lensing potential and the big phi for the metric perturbation. So the CMB lensing potential can be inferred from metric fluctuations along each line of sight with a relation that you know very well if you work in cosmic shear. It's always the same relation that applies to all weak lensing phenomena. You can write the lensing potential in one direction as an integral along one line of sight of the metric fluctuations on this line of sight multiplied by some kernel or some window function, which is universal for lensing. And it knows about the Einstein radius and all these things. So similar as for galaxy weak lensing experiments. But this gives you a projected lensing potential map that you can expand in spherical harmonic, and you get some phi LM coefficients. And these phi LMs are very easy to compute with an Einstein-Boltzmann solver. And it's a basic task in Camber class to take the metric fluctuation, to perform this integral, and to get the power spectrum. The equations are very similar to those giving rise to CLTT or CLEE, just with a different source or integrand in your line of sight integral. So we know very well how for a given cosmological model, we can predict this lensing power spectrum. And given the lensing power spectrum, you can estimate what is a typical amplitude of a multipole. You can also then estimate what is a typical magnitude of these deflection fields, and it's typically of the order of a few arc minutes. So it's very small, and it means that the lensing will have no effect on big patterns, big angular scale on the CMB map. It will only have an effect on relatively small angular scales. Okay, so there are many important goals when you work on CMB lensing. There are many things you would like to do. First, you would like to understand how the CL of temperature and polarization that we computed before are affected by lensing. They should be distorted by lensing. And if you don't know how they are distorted, then when you fit your SPT, ACT Planck data, you may do a mistake, because you will fit the unlensed spectra to the observed lens spectra. So there will be a mismatch, and maybe you will try to compensate this mismatch by biasing artificially your cosmological parameters. Even if the effect is very small, you don't want this to happen, because even if the effect is very small, it could be comparable to the very small error bar on the measurement of the CLs. So that's the first task, to be able to predict not only the unlensed CLs, but also the lensed CLs. Then ideally, you would like to find a way to analyze your data and reconstruct the map of the lensing potential. And we will see that this is possible using a non-Gaussian estimator. This is a CMB lensing map reconstructed by Planck. There are even nicer ones that have been obtained by ACT and SPT nowadays. If you can get such a map, you can expand in ALMs and compute the lensing potential. And that would be very nice, because we know how to predict the lensing potential. So that's one additional independent information. We could fit TT, TE, EE, maybe BB, and the lensing potential, and learn more about cosmological parameters. The red points, again, my slide was not updated, are the measurements of CL55 from Planck. We have much nicer ones now from ACT and SPT. But if you have your map, then you can predict what was the deflection field in each individual direction. And knowing this, you can do an inverse transformation and try to understand what was your delta rho map. And this is called delensing. You can clean the observed temperature and polarization map from lensing deflection and reconstruct what the map would be originally. And then you can compute the spectrum of the maps. That would be the spectrum that you would get without lensing. Of course, you can do this only up to some error. But there is a method for doing this, and it's particularly useful for the BB mode, because by delensing your BB map and computing then the CLBB, ideally, you would get rid of this green curve. All this delensing business always has a theoretical error that you cannot beat, and also some error coming from the noise in the measurement. So it's never perfect, but it allows you to gain maybe an order of magnitude, decrease this signal by an order of magnitude. You would be just left with a residual, and get a better handle also on smaller values of the primordial CLBB. So this is very challenging, and if you work on the field, you probably know more than me on it. If you don't, I will try to walk you through the main equations in the last 10 minutes before we finish. The basic method is the following. So I take X to be either the temperature field or the E polarization field or the B polarization field. X could be T, E, or B. And I write, as before, that my X observed is the X rho deflected by the gradient of the lensing potential. This is small, so I can Taylor expand. At first order, I get this. At second order, I get two derivatives. For some applications, the second order is needed, as you will see. Here I am working on the sphere. Instead of working on the sphere, I can go to harmonic space. I can do a spherical harmonic expansion of all functions and write that my observed multiples, XLM, are from here the row 1, and then each term will give me some complicated linear combination with some coefficients multiplying here 1 phi lm and 1 x rho lm, and here 2 phi and 1 x. And these coefficients here are horrible. They have the infamous Wigner function inside, and they are computationally very heavy. So I will start from here, and I will not tell you how to do all these things. That would be too long, but just the first two. I hear some background noise. I think you are getting tired. Just try to concentrate 5 more minutes. Background noise from knees, actually. Surprisingly, you can average this out and feel something. Okay. Try to remain concentrated 5 more minutes. How do I compute my length CLs? Well, I start from this equation, and now I take the variance of x. If I want to compute, for instance, the length CLTT, I will take 2 TLM ops, multiply these two, take the variance, and I will treat x rho and phi lm as 2 Gaussian fields with some variance that I know. They are the spectrum of CLTT or CLX and the spectrum CL phi phi. They are so they are both Gaussian. They are uncorrelated because the x are fluctuations living on the last scattering surface. The phi reflect fluctuations on cluster scales. So my x and phi are uncorrelated. So when you do this, you see that you need to keep the j term, because if I compute an XLM correlated with another XLM, I will get first a term with 2 x rho, and this will be my unlength spectrum. Then I will get term with 1 phi and 2 x rho. But when I will take the average of phi x rho, okay, I will realize that because these variables are uncorrelated, I can decompose it in this way. This is a spectrum of xx, but this is 0 if phi is a Gaussian variable centered in 0. So this order will vanish. At the next order, I can use 2 such terms to get a phi square x square, or I can get this term times this term to get a j phi square x square. And these 2 terms are of the same order of magnitude and contain 1 CL of x and 1 CL of phi. So I get a relation like this, and this is how you compute your length spectrum. It's a very heavy calculation, so different people have devised different approximation scheme to do it in a numerically efficient way. And all modern codes use a method of Lewis and Chalinor, which is really very, very good. This is implemented in common class, and it gives you the observed CLs, the length one, as the unlengthed one smoothed by a kernel that depends on CL phi phi. And I show you the difference now between the length and unlengthed CLs. In red, I have my unlengthed CLs. In black, I have the lengthed ones. And it really looks like the result of lengthing in the sense that on intermediate scale, there is less contrast between the maxima and the minima. And when I go to very small scales, because I have this fast dropping tail, the running smoothing kernel on the curve gives you like a slightly smaller amplitude. So at very high L, it's like lengthing would generate more signal. It's not really a generation of more signal. It's more some amplitude moving from the left to the right. And so what we should fit to the data is actually the black curve, not the red curve. Otherwise, we could bias our reconstruction of the scalar tilt, for instance. Okay, I'm not sure I have time for the last point. The last slide was here and was going to explain the quadratic estimator, but I think we are running out of time, so this could be a question. Otherwise, I will stop here. I will flash again this slide showing all what you can do with CMB lensing, and I will take your questions. Yes, exactly. So the Einstein radius says that the weak lensing of a source is influenced by all the intervening matter, but especially the intervening matter, which is at half the physical distance to the source. And so this is true here. And this kernel that we are using here is different, has the same shape for CMB lensing and for galaxies, but it depends on the distance to the source. And here the distance to the source is a radius of the last scattering sphere. And it makes this kernel sensitive to structures at higher redshift than galaxy shear. You can have in mind the fact that you are sensitive to all structures between 0 and 3. There is not a clear peak because lensing effect is maximal when you are at half the distance, but this is compensated by the fact that structure keep growing and that you have more nonlinear structure close to you. So this kernel at the end is pretty flat between something close to 0 and 3. Especially between 1 and 3, it's pretty flat. And so this CMB lensing reconstruction gives us a handle on structure at really large redshift and is very complementary to weak lensing experiments. So ideally, if you have measured your CL55, you will analyze it together with a tomographic analysis of cosmic shear survey, and this would be your last redshift bin. And then you would get a nice like video of the effect in time of neutrino free streaming or things like this. Not very important. So that's a brilliant question. And to answer quantitatively to your question, what I could do is compute the lensing effect here or compute CL55 directly. Either using linear perturbation theory or some nonlinear perturbation theory. For the nonlinear perturbation theory, you can use HM code, allofit, or EFT of LSS. And then you realize that the impact is non-negligible, but extremely small. So it means that you need to take the nonlinear correction into account, but you don't need to be accurate. Even with a quick allofit estimate, you get your answer. So making a precise calculation of nonlinear effect is not a challenge within ACT or SPT. I'm not completely sure, but I don't think so, because it would, okay, it's true that it's gradually important when you go to high L, and we will have better and better error bars, tempered by an increase of the error bars coming from template fitting of foregrounds. At the level of CL55, we will never be sensitive to too large L either. So no, I think I agree that for Simon Observatory, you probably need to control your errors on the nonlinear corrections a bit better, but it will never be some crucial issue like for Euclid or LSST. But still, since we are all making a lot of progress with algorithm implementing EFT of LSS, and since these are Mildy nonlinear scales, I think it would be nice to compute this nonlinear correction from in a theoretical way instead of doing like now where everybody is using HM code. Yeah. But no, I don't think it's a big issue. Yeah. Yeah. Okay, thank you. Okay, step 2, I will try to be concise. So this we have already seen. So this is a very important equation explaining the effect of lensing. Now I want to infer the lensing potential. And so I want to infer this coefficient phi Lm. So for this purpose, you can neglect this order, focus on this part of the equation, and you would say, okay, I would like to invert this relation and get phi Lm on the left. You cannot do this because you measure Lx ops, but you don't measure Lx rho. So you don't know X rho, so you have to work harder. And the idea will be to exploit the fact that this term is making the observed field non-Gaussian. Without lensing, you would have a Gaussian field. Now you introduce some non-Gaussianity. So your dream is to build an estimator of this non-Gaussianity that will single out the role of the lensing. So a few more steps. To do this, I will take two of these equations for two coefficients, xlm and yl prime m prime. I don't keep the same letter because I could do it with two temperature multiple, but I could do with one temperature and one polarization multiple and different LMs. I just do the multiplication. I have my leading order contribution, and then I group the term of order 1. I have a kernel with a phi and 2 rho x. And now imagine that you do something that you cannot do in reality. You assume you have a fixed large-scale structure field, a fixed phi, but you average over all possible realization of the CMB, just for academic purpose. So I take this CMB average, and this will give me the unlensed spectrum if the two indices are the same. But if the indices are different, which I assume here, this will be 0. And then I will be left, also this will give me the CLs of x and y, provided that the indices are the same. So my CMB average gives me a big kernel times the CL rho times phi Lm. And again, I would like to measure phi Lm from here, but I cannot do this CMB average in reality. But this is a situation which is very close to the situation when we were just trying to measure the CL spectrum. Because the theoretical spectrum was the ALM squared in such a perfect idealized averaging over many realizations. And since we cannot do this average, we said that we are going to estimate the CLs by taking the average over many realizations of the observed ALM. Okay, and because we have averaged over 2L plus 1 values of M, we have a 2L plus 1. By doing this, we built what we call an estimator of the CLs. We don't do the CMB averaging, but because we average over many realizations of the theory, we get a good estimate of the CLs. And here it's the same. You cannot do this average, but you can measure many such products for many LMs and combine them into a way that the combination would give you this phi LM. And to do this, you just have to go back to here and to find a coefficient that will allow you to make a linear combination of this x and y. And this coefficient should be chosen in such a way to cancel the kernel, so it should be orthogonal to this kernel, and it should include a division by this spectrum in order to remove these coefficients. And when you build such a combination, you build an estimator, it's a sum over many x, L, M ops, y, L prime, M prime ops, with a very complicated coefficient here, which is chosen such that the average of this sum over many realizations is one single phi L1 M1. So you do this just by algebra, by trying to invert this algebraic relation. And this is what Yu and Okamoto did in 2003. This is how they derived their quadratic estimator. Why is it called a quadratic estimator? Because to estimate it, you need to multiply two multiples. So you need to start from two maps. So you extract phi from the square of maps in a way. But you have a lot of freedom. You can build an estimator for temperature, times temperature multiples, or T times E, or E times E. You can take all the combinations you want. Each of them will give you an estimate of phi LM. And if you know the noise of your experiment in different components, noise for temperature, noise for polarization, etc., you can always find the best combination of all these optimators that will give you the best measurement of phi LM with the smallest cosmic variance. So that's the idea of the quadratic estimator. There are more sophisticated techniques, but they all rely on essentially on this idea. So what you do is that you exploit the non-Gaussianity induced by weak lensing, because if I would take the CMB average for L and M different from L prime and M prime, if I did not have lensing, only this term, it would vanish, right? Because if LM and L prime and prime are different, these two terms should be uncorrelated for a Gaussian field. But because I have lensing, I have introduced a non-Gaussian contribution. And so I exploit this non-Gaussian contribution, this non-Gaussian nature of the observed map to extract my phi LM. That's the idea. Yeah, yes, of course. There is a very intuitive reason. It's because the effect is dominated by high redshift and large scales. It's very big clusters at very big redshift. Yeah. Yeah. A physical explanation of how? Ah, yes, 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 yes. Very good, very good, very good, very good. Okay, up quickly. Yes. Okay. So the goal is to convince you that after decoupling, when your photon are now free streaming and not interacting, you go gradually from a situation where you mainly had a monopole and a dipole to a situation where the non-zero multipole have a higher and a higher L. So you have created from inflation your pattern with maxima and minima of density. And when you live in the early universe at a random point, say here, I will take here, okay? The photons initially have a tiny mean free path. So the photon you see come from points which are infinitely close to you. And so they all have the same temperature, and you have a monopole. Then at the approach of recombination, the mean free path of the photon increases. And so typically the photon that you would measure as an observer in the early universe would come from a larger sphere. And at some point in this sphere, you would have photon coming from an overdensity, photon coming from an underdensity, you would see a dipole. Then time passes by and your last scattering sphere increases, and it will cut through quadrupole components, and then octopole, etc. And then we reach a situation today where the last scattering sphere is very big, and you have excited up to L's of 3,000 or so. And so this explains why when time passes by, you excite theta L's with larger and larger L's. But why do you de-excite the L's with the smaller L's? Because now when my last scattering sphere is very big, if I want to see the dipole pattern on this sphere, I have an averaging over all these fluctuations, and the dipole averages out. So you are continuously seeing a larger last scattering sphere, and this tells you that you are continuously seeing larger multiples with larger L's, while averaging out over the multiples with the smaller L's. And this is encoded in the structure of the Boltzmann equation, which has a coupling to nearest neighbors. And when you solve this equation, you realize that if initially you only populate theta 0 and theta 1, through this structure, the power gets transferred to larger and larger L's. And so if you would plot theta L as a function of L, you would start from something like this, and then you would have a peak moving to the right. Yeah.
Okay. I don't see any more questions, so yeah, there is one.
You should not start by excusing yourself, right? Okay. You are a desperate case then. Yeah, okay. So that's so I didn't go at all into the observational field and all the difficulties of map making, and it's very, very complicated. And in particular, at the end of the day, once you have finished an experiment, you need to produce a likelihood, which is, as usual, the likelihood of the data given the theory. And depending on the L's you are looking at, so it's a very computationally expensive problem. So you cannot apply the ideal method from scratch. You need to find some strategy to make the problem tractable. And depending on the scale you are looking at, you will use different strategies. And so the strategy used to produce a likelihood in Planck at low L and at high L is completely different. At low L, you fit directly the pixels of the map. At high L, you fit the spectrum with a combination of primordial signal and foreground templates. And this is why the likelihood is cut in two pieces with an intermediate value of 30, I think. Yeah.